Elementary data structures. In this chapter, we will delve into the foundation of dynamic sets represented using simple data structures involving pointers. These structures form the cornerstone of many advanced algorithms and systems in computer science. Although pointers allow for constructing complex structures, we begin with rudimentary yet essential ones: arrays, matrices, stacks, queues, linked lists, and rooted trees. Dynamic sets are collections of elements that can grow, shrink, or evolve over time. By understanding these elementary data structures, we can efficiently manage, store, and manipulate data to solve problems across domains like scientific computing, databases, and real-time systems. Throughout this presentation, we will explore their representations, operations, and use cases, enabling a deep appreciation for their versatility and relevance in computing. Arrays. An array is one of the simplest yet most efficient data structures. It is stored as a contiguous block of memory, allowing rapid and direct access to elements. This property makes arrays an ideal choice for tasks requiring predictable memory layout and high-speed access. Accessing elements in arrays is performed using index calculations, which are computed in constant time. Most programming languages mandate uniform element sizes within an array to facilitate consistent memory addressing. However, when elements vary in size, arrays may store pointers instead, ensuring flexibility while maintaining efficiency. Arrays are fundamental for building other structures like matrices, stacks, and hash tables, showcasing their foundational role in computer science. Matrices. Matrices are extensions of arrays into two-dimensional or higher dimensions. They are commonly stored in either row major or column major order. In row major order, rows are stored sequentially, while column major order arranges columns contiguously. Each approach has its computational advantages depending on the application, such as data traversal patterns and numerical simulations or image processing. For efficient memory use, single array representations of matrices are often preferred, though multiple array strategies may enhance flexibility. For instance, ragged arrays, where rows or columns vary in size, allow dynamic configurations suited to irregular data. Block storage further optimizes access by dividing matrices into submatrices, which are processed in localized groups to improve performance in large-scale computations. Matrix representations. Matrix representation significantly influences computational performance. Single array representation stores all elements contiguously, making it optimal for operations requiring sequential access. Multiple arrays, on the other hand, organize rows or columns as independent entities, adding flexibility but at the cost of pointer overhead. Block representation subdivides matrices into manageable chunks, particularly useful for parallel processing or cache optimization. Applications in graphics rendering or scientific computation often leverage such techniques to handle vast datasets efficiently. Each representation method serves specific use cases, emphasizing the importance of aligning the representation with problem requirements. Stacks. A stack operates on the last in, first out, LIFO, principle. This structure is akin to a stack of plates, where only the top plate is accessible. Two primary operations define stack functionality: push, which adds an element, and pop, which removes the top element. Both operations execute in constant time, offering excellent performance for nested computations or function calls. Stacks are implemented using arrays with a pointer tracking the topmost element. Overflow occurs when pushing beyond the array size, while underflow arises when popping from an empty stack. These boundary conditions must be managed carefully to maintain robustness. Stacks are indispensable in recursion management, expression evaluation, and parsing algorithms. Stack operations are fundamental to using this data structure effectively. There are three key operations: stack empty, push, and pop. Stack empty is used to check whether the stack is empty. If the top pointer is 0, this operation returns true, otherwise, it returns false. Push adds a new element to the top of the stack. The top pointer is incremented, and the new element is stored in the corresponding position in the array. On the other hand, pop removes the topmost element from the stack. The top pointer is decremented, and the element is effectively removed. Each of these operations executes in constant time, which is O of 1. However, error handling is crucial. If you attempt to pop an element from an empty stack, this results in an underflow error. Similarly, trying to push an element onto a full stack results in an overflow error. Stacks are frequently used in scenarios such as function call management, expression evaluation, and backtracking algorithms, emphasizing their importance in computational processes. Queues are another essential data structure, operating on a first in, first out or FIFO principle. The two main operations associated with queues are enqueue and dequeue. Enqueue adds an element to the tail of the queue, while dequeue removes an element from the head. This ensures that the order of elements is preserved as they are processed. Queues are typically implemented using arrays, with pointers indicating the head and tail positions. When the tail reaches the end of the array, it wraps around to the beginning, creating a circular queue. This implementation maximizes space efficiency. Handling edge cases, such as when the queue is full or empty, requires careful consideration. Queues are widely used in operating systems for task scheduling, network data buffering, and breadth-first search algorithms. Queue operations involve specific steps to manage the flow of elements effectively. Enqueue inserts an element at the tail. If the array is full, the tail pointer wraps around to the start, maintaining the circular structure. Dequeue removes the element at the head, advancing the head pointer to the next position. These operations are computationally efficient, each taking constant time, or O of 1. Error conditions like underflow, which occurs when dequeue is called on an empty queue, or overflow, when enqueue is attempted on a full queue, must be managed appropriately. These operations ensure that queues remain reliable for tasks such as processing requests in a web server, managing print jobs, or implementing simulations where order is critical. Linked lists are dynamic data structures that provide flexibility over arrays. Unlike arrays, linked lists do not require contiguous memory allocation. Instead, each element, or node, contains a pointer that links it to the next node in the sequence. This design allows linked lists to grow and shrink dynamically, making them suitable for applications with unpredictable memory requirements. There are several types of linked lists: singly linked lists, where each node points to the next; doubly linked lists, where nodes point to both their predecessor and successor; and circular linked lists, where the last node connects back to the first. Linked lists are widely used in scenarios requiring efficient insertions and deletions, such as implementing stacks, queues, and graph representations. Operations on linked lists are straightforward yet versatile. List search is used to find a node containing a specific key. This operation involves traversing the list and takes linear time, or O of n, in the worst case. List insert allows the addition of a node at a specific position. In doubly linked lists, insertion is efficient, taking constant time, or O of 1, as it only requires pointer adjustments. List delete removes a node by splicing it out of the list, also in constant time for doubly linked lists. The efficiency of these operations makes linked lists ideal for dynamic data management. They are particularly useful in applications where the size of the dataset is not fixed, and frequent insertions and deletions occur. Examples include implementing adjacency lists for graphs, dynamic memory allocation, and undo functionalities in software systems. Sentinels are special dummy objects used in linked lists to simplify boundary conditions. In a doubly linked list, the sentinel replaces nil and connects the head and tail of the list. This structure eliminates the need for explicit checks for empty lists or edge cases at the head and tail during operations. The sentinel node contains all the attributes of a regular node but is never part of the actual data. Using a sentinel transforms a regular doubly linked list into a circular one, where the sentinel serves as both the predecessor of the head and the successor of the tail. Operations such as insertion and deletion become more efficient because they require fewer conditional checks. While sentinels simplify code and reduce the risk of errors, they consume additional memory, which may be significant for applications managing many small lists. Binary trees are hierarchical structures where each node has a key and up to two children, a left child and a right child. Each node also maintains a pointer to its parent, with the root node having no parent. Binary trees are widely used for efficient searching, sorting, and hierarchical data organization. If a node has no children, the corresponding left or right pointer is set to nil. The root node is referenced by the attribute t.root. Binary trees are the foundation of numerous advanced data structures, such as binary search trees and heaps. Their efficient traversal and manipulation capabilities make them indispensable in database indexing, file systems, and artificial intelligence applications. Rooted trees with unbounded branching require a representation that accommodates varying numbers of children. A common approach is the left child, right sibling representation. In this scheme, each node maintains two pointers, one to its leftmost child and another to its immediate right sibling. This design allows the representation of any n-node tree using O of n space. This representation is particularly advantageous for applications where the number of children per node varies significantly. It ensures efficient traversal and minimizes wasted memory. Examples include organizational hierarchies, XML document structures, and game trees, where nodes often have different numbers of children. Other tree representations are tailored to specific applications. For example, heaps, which are complete binary trees, are often represented as arrays. This representation leverages the compact nature of heaps, storing elements contiguously and eliminating the need for explicit pointers. In cases where trees are traversed only toward the root, parent-only pointers are sufficient, saving memory. Many other schemes, such as binary space partitioning trees for graphics or KD trees for spatial searching, cater to specialized needs. Selecting the appropriate representation depends on factors like traversal patterns, memory constraints, and the types of operations required. Choosing the right data structure is crucial for solving computational problems effectively. First, consider the problem requirements. Understand the operations you need to perform most frequently and prioritize data structures optimized for those operations. Next, evaluate space constraints and time complexity to ensure that your solution is both efficient and scalable. Implementation simplicity is another key factor. A data structure that is easy to implement and maintain reduces the risk of bugs and facilitates future modifications. By balancing these considerations, you can select the most suitable data structure for your application, ensuring optimal performance and maintainability. Understanding elementary data structures is fundamental to designing efficient algorithms and systems. From arrays and linked lists to stacks, queues, and trees, these structures provide the building blocks for solving complex problems. Selecting the right data structure involves balancing factors like time complexity, memory usage, and implementation effort. By mastering these foundational concepts, you can approach computational challenges with confidence and creativity. Whether optimizing search algorithms, managing dynamic datasets, or organizing hierarchical information, these tools enable you to design solutions that are both elegant and effective.